Thank you. It's a great opportunity to be here, and thanks for the organizers for the invitation. I will present actually two algorithms in the context, of minimization of convex lower semi-continuous function, proximal type algorithm, and in the context of in connection to minimization of a differentiable function, a gradient type algorithm. And the setting is the following: we have a Hilbert space, Hilbert space H with usual scalar product and norm, and we consider this problem, minimization of a function, global minimization problem where f is a convex proper lower semi-continuous function, and we assume that the set of minimizers is non-empty, and we want to find rapid methods to the element of the minimum norm of this arcing set. And first, one of the first attempts, it was this algorithm, it's an inertial proximal algorithm. In this paper, written jointly with the late Professor Atush. And in this algorithm, we take, the inertial parameter with is quite common. We took this Tikhonov regularization parameter, and we call that a proximal operator. It has this form and can be written as a resolvent operator of the subdifferential, and therefore the algorithm can be reformulated this way, as a differential inclusion. And we need actually this to can define this subgradient. Yeah, we define this subgradient as the subgradient for which we have equality here. Because we will give also rates for this subgradient. And the results what we obtained in case when alpha is greater than 3, and for every s belonging to this interval is that we have some pointwise estimates, for the potential energies, let's say, for the little o k or minus 2s, which is quite good because s can be as close to 1 as we want, for the discrete velocity, and also for this subgradient. And we also obtain some estimates. S does not belong to the algorithm. And for areas, we cannot give a better upper bound actually. It depends by this, one, It's true for areas. Of course, we want to be very close to 1. It's not sharp, let's say. Some estimates and a strong convergence result where x star be a minimal norm element from this argument set. Then we have this Leibniz is equal with 0, which means that xk, the sequence generated by the algorithm has a convergence, a strongly convergent subsequence to x star. And in some cases, we have actually full strong convergence, but when xk is in the ball or the complement of this ball, but this condition cannot be a priori verified. Yes, it's some very complicated conditions. So my starting point was this algorithm, and I said that let's put in the parameters, more generalized form, the inertial parameter. Let's take in this form, when q is between 0 and 1. When q is 1, the inertial parameter is the same as the previous algorithm. The Tikhonov regularization parameter epsilon k be of this form. Also here, when p is 2, then we have the same Tikhonov regularization parameter, and also consider a variable step size here, lambda k, which is still this form of polynomial form, and we put actually these parameters in order to show the correlation between these parameters. They are so strongly correlated, and actually we have many settings, but we have three main settings of the parameters when we can obtain weak convergence at very fast rates. a setting when we can obtain strong convergence results, and a setting which separates the two cases. More precisely, okay, when we have this case that P is greater than Q plus 1 and delta is greater or equal than 0, we have several subcases, but we have for this potential energy arbitrary rate depending by the step size. Okay? And we have a weak convergence of those sequences generated by the algorithm. And we treat also the case that Q equal with 1. And it can be seen that Q equal with 1, there is also correlation between alpha and the delta. And this means that if we fix the inertial parameter alpha, then we do not obtain an arbitrary rate, for instance, for this potential energy. And this means that actually Q less than 1 might be in some sense better to consider, yeah. Okay, and also we have also this case when Q is less than 1 and P is greater or equal to 2, and we have these rates, but we don't have any convergence results. So this is one of the main cases. The second one is quite the opposite of this, when we have P is less than Q plus 1 and delta is less or equal than 0. And in this case, we obtain strong convergence results. Actually, okay, when delta is quite very negative, say we obtain that it's bounded. When delta is between 0 and this P minus Q minus 1, okay, it's negative number, then we obtain this limit. But in case when the step size is 1, we obtain full strong convergence of the generator sequences. Yeah. Convergence is also quite good rates. I mean, okay, here Q is less than 1. P can be very close to 2, and almost the order 1 over k square is the rate here. Okay, and we have another case which is separates the two cases. The cases when you obtain weak convergence and strong convergence. The case when P is equally Q plus 1 and delta is arbitrary. And also in this case we cannot say anything about xk. Okay. But we have also in this case quite good rates. Okay, of course this is a rate when for instance delta is greater than minus Q minus 1. Okay, so in this case, okay, actually these are the results for this proximal algorithm with a regularization terms, and okay. And we see that we had a comprehensive analysis and covered almost everything, almost all the cases. It's not covered the case when P is less or equal than 1, for instance. The second part of our presentation, we consider a minimization problem. Okay, where f is a convex continuously differentiable function, a full function with Lipschitz continuous gradient. Okay. Also here we want to design an algorithm which converges strongly to the minimum norm minimizer of the function. And in this case, we want to preserve as much as possible Nesterov-type rate for the 1 over k square for the potential. And yeah, we recall a Nesterov algorithm, which can be written in this form, where the step size is between 0 and 1 over L. L is the Lipschitz constant of the gradient. The inertial parameter has this form. It depends by a second tk, and tk is given by this recursion. Yeah? Tk plus 1 is equal with this one, and it is known that in this case, okay, the result of Nesterov, in this case, fxk minus, okay, the minimum, it's for the 1 over k square. However, whether the sequence is generated by this algorithm, if converge, even in the weak topology, it is not known. And fortunately, a slight modification of the inertial parameter will assure weak convergence of the generator sequences. More precisely, if we consider, okay, here not equality but inequality, this kind of sequences, okay, satisfy this inequality for R less than 1 over 2. Okay, and that's why in the literature tk is usually taken in this form. This means that R is 1 over alpha minus 1, and this will force that alpha is greater than 3. And okay, in this case, algorithm, okay, modified Nesterov algorithm can be written in this form. This is the inertial parameter. And in contrast to the original Nesterov algorithm, the sequences generated by this algorithm converge in the weak topology of H to a minimizer of the function. Okay, and actually we have this okay, this potential energy has order little o k on -2 k square. This is in case when alpha is greater than 3. And alpha is equal with 3. We don't know whether the sequences converge. And actually here we have the capital O rate, the big O rate here for this. So this was actually the algorithm, our starting point actually. We take this algorithm but without specifying the inertial parameter, okay, and it can be regularized in several ways. I mean, we can put theorem of regularization term here, or here, and inside of the argument of the gradient. And actually, we tried this, okay? First attempt was to put here a theorem of regularization term. And we could not obtain anything notable, I mean, anything new. Second, it was to put here in the argument of the gradient, because we have seen that proximal, for the proximal algorithm we have the argument of the prox. But neither this we did not give anything notable. Of course, we can put also here, and if you put here a theorem of regularization term, will appear also in the argument of the gradient, okay? So here, of course, but here. But neither this is wasn't enough. And finally, we put here a theorem of regularization term, but the form S epsilon k y k, because in if you take this theorem of regularization term, then we have that this is a gradient of a strongly convex function. Okay, but still this is not enough. And we will show that this is not enough. We are numerical example. We will need also a theorem of regularization term here put into in the definition of y. I have an example which shows that if we don't not use this, then we don't have convergence to the minimal norm solution. Okay, so in this case, we can obtain strong convergence generated to the minimum norm minimizer. Of course, that we need the form of these sequences bk and ck, and you have a quite complex form. And okay, so we consider this algorithm, okay, in this paper jointly with Mihaly Karapetians, who's here, the doctoral student of Professor Botz. And okay, we wanted to obtain strong convergence, and for this we need the form of these sequences bk and ck. We assume a priori that S belongs to this interval 1 over L. L is the Lipschitz constant of the gradient. Ck is a non-negative sequence which is satisfied that the limit is 0. Okay, goes to 0 when k goes to infinity. Epsilon k is a non-inclusive positive sequence and goes to 0 when k goes to infinity. The form of these sequences are crucial in order to obtain our results. And if you remember that the Nesterov algorithm, the inertial parameter has been given in a function of a tk sequence. Yeah. Also here we will need another sequence qk which will satisfy this condition. And with the help of this sequence, we will give the parameters bk and ck. Okay, this condition which is quite ugly, but actually this condition is very similar to the original Nesterov condition. We can show this very shortly if we take epsilon k 0. Okay, we take qk of this form, then condition q is equivalent with this, or more precisely, it's equivalent that tk plus 1 belongs to this interval, and we can take actually tk plus 1 equal with the upper bound here, and in this case we have also satisfied that tk is greater or equal than 1. Okay, And can we see that the difference actually this is okay, the recursion for the Nesterov sequence, okay, and this is condition, yeah. And also the step size. dk and ck we will define with the help of this condition. So, not precisely, we set the step size, okay, so consider that. Okay. Set the step size and also epsilon k. And after that, okay, we need a sequence which satisfies this, and with the help we will define bk and ck. These are the here are the define bk and ck with the condition b and c, okay. Quite complicated, but actually from a practical perspective, it's quite easy to implement this. In, okay. And okay, it can be seen that it depends by qk and also s and epsilon k. And in this case, okay, we consider actually at qk, okay, satisfying q, bk and ck given by this condition b and c, and we consider that s and the epsilon k is already is given. So the algorithm, okay, we have an algorithm, and let xk and yk be the sequences generated by this algorithm. And we must assume some other okay, like other things. I mean, this sequence must be bounded for k bar big enough. But this is not a restriction. Usually, this sequence goes to 1. I mean, it's convergent to 1. This sequence must be increasing and has its limit infinity. This is a restriction, but okay, there are many sequences satisfied in this. Okay, and also we have that this limit must be 0. Also, this will give a restriction on q. Okay. But in this case, we have strong convergence. Okay, it's satisfied. We have strong convergence of xk. Okay, for the minimum norm minimizer x star, which is a projection of 0 to the arm itself. But at the same time, we have that this difference is order 1 over, okay, square root epsilon k, and epsilon k we know that goes to 0. So we got that also yk converges strongly to x star. And for the function values, we have this estimate in xk, okay, and in yk. And also for the gradient, okay, the discrete velocity, okay, it was expected, and the gradient. This is abstract result, and what happens if we specify epsilon k? We specify epsilon k of this form, c and k on yeah, and qk. If you take qk of this form, okay, and this q, the exponent can be between 0 and 1, can be also 1. Then this condition q is satisfied for every step size. And okay, in this case, algorithm is this way, which I said that it's very complicated, but actually it's easy to be implemented. This is the inertial parameter bk minus 1, and this is the Tikhonov regularization parameter ck. Okay. And also here we have epsilon k. And this is a particular case of algorithm AP. And we can say that ck in this case is not increasing and goes to 0. So indeed, this term is a Tikhonov regularization term. And the assumptions that this is bounded holds trivially, of course. That this is increasing and its limit is infinity. Will give that p is less than 2q, yes, because yeah, 2k square epsilon k goes to infinity. It means that 2q is less or greater than p. Okay. And also that this limit goes to 0. It means that q must be less than 1. And we have, in this particular case, we have the following result. So if we have q between 0 and 1, p between 0 and 2q, a fixed step size s belonging to this interval, we consider the sequences xk, yk generated by algorithm. Then xk and yk converge strongly to the minimum norm minimizer of f. We have these estimates for potential energies, okay, for the velocity, okay, discrete velocity, and for the gradients. Can we see that P, okay, Q can be as close to 1 as we want, and that's why P can be as close to 2 as we want, and this is almost Nesterov-type. Not 1 over K squared, but P is very, very close to 2. Yeah, almost Nesterov-type. Okay, and we also show some numerical experiments. We take a class of function, but very, very simple functions. We know that they have Lipschitz constants in this form. For this function, okay, the minimum of f is 0. The Arbin set is okay, it's a line, okay, from R square, and the minimal norm solution is 0. So we don't want to resolve this. We want to show that our algorithm is okay, the behavior of our algorithm. And we take okay QK, the step size, and some starting points, and also we take several Tikhonov regularization parameters, okay, this form. And also take the for when we don't have Tikhonov regularization, and because the order of convergence for discrete velocity and this potential energy of 1 over K and 1 over K square respectively, and then we also represent these values. And what we can be seen that okay, we have very good results, and P is closer to 2. Yeah. Results, and okay, this is the result when you don't have Tikhonov regularization. Okay, which actually here we show that actually the presence of Tikhonov regularization can accelerate the convergence. But what is very important is to see what happens if we reduce to the Tikhonov regularization, one of the Tikhonov regularization terms. And for this, first we represented the sequence xk, okay, which has 2 components, okay, the first component, the second one. In case that we don't have Tikhonov regularization, and can be seen that they are not converging to the minimum norm solution because the minimum norm solution is 0, 0. And in case we have both regularization, actually we have convergence to the minimum. So in case we don't have Tikhonov regularization, okay, we don't have strong convergence, but neither if we don't have this Tikhonov regularization term. In case that we renounce to this term, okay, epsilon k is 0, actually ck will become this term, and of course ck will remain a Tikhonov regularization term, but we don't have strong convergence anymore. And which is very interesting, that in case that we renounce to this term, okay, we still don't have strong convergence to the minimum norm solution. So we need this Tikhonov regularization in the definition of the sequence yk.